I just give a brief overview regarding what is the interaction and why there is a confounding, and also how to find the confounding structure. Takuchi proposed an interaction table, so we don't need to do a very tedious analysis, and we can understand what will be the confounding structure, which is called interaction table. For each orthogonal array, there is a corresponding interaction table. This is the interaction table for L8. As you can see, it's on the right side. The interaction table might have a different format. This is one of the most popular format you can see. It's a triangular shape, and I already tell you how to find the interaction. For instance, if you are putting one factor A in the column 1 and another factor B in column 2, like here, where is the interaction AB will be? From the table, right here, you A put in column 1, B in column 2. So from the right table, starting from horizontal 1, and then you look at the vertical 2. Therefore, the interaction for any factors in 1 and 2 will happen in column 3, right here. This is how you use the interaction table. Therefore, for any arrangement, this is one of the examples we saw last week. If you put factor A in column 1, factor B in column 2, and factor C in column 4. This is the design of experiment for 3 two-level factors arranged in L8 orthogonal array. Then you can use the interaction table to find the complete confounding structure. This is the L8 interaction table. Then we need to find out how many interactions will that be. And I show you that one of the easiest way you learned before to find the number of two-way interactions is use the combination C, M by N, M, N. And which is, if I recall correctly, this is the equation for combination. For instance, we have 3 factors, and we want to find out how many two-way interaction will that be. In this case, will be C3 by 2, which is, by using this equation, will be 3 over 2 minus by 3 which is okay. And you will know there will be 3 two-way interaction, 3 type of two-way interaction. Should be very easy. AB, AC, and BC. By using the interaction table, you can find out where are those interactions. Starting from, for instance, column 1 and column 2. You put A in column 1, B in column 2. So the interaction between column 1 and column 2, by using the interaction table, we know it will happen in column 3. So here, column 3 will be the interaction of column 1 and column 2, which will be A cross B, the interaction AB. Using the same thing, what will be the interaction AC, which is arranged in column 1 and column 4? So by looking at the table, column 1 over here, and column 4, all the way down here, you will see is happening in column 5. So right here, the interaction between column 1 and column 4 will happen in column 5. So you find out all the interaction AB, AC, and BC, and arrange them into the table. We call this is the confounding structure. So for your confounding structure, you need to put all the interactions, including all the main effects, into this table, and you will find out what will be the confounding? In this case, there is no confounding between main effects and interaction, right? Main effects ABC, interaction AB, AC, BC. They are all separated, no confounding, which is good, which means that if you arrange your design using this way, you can use the interaction plot to find out how strong the interaction AB, AC, and BC. If you are three-level design, in this case, L9 is for three-level factors. In case you put A in column 1, B in column 2, what will be the confounding structures? On the right side is the interaction table for L9. It is a little bit different from the interaction table for two-level factors. You can see for column 1 and column 2, the interaction will happen in 3 and 4, 2 columns, not just 1, 2 columns. Why? I will talk about that later. Since what do I mean by, okay, I will talk about that later. And as you can see right here, the interaction AB will kind of distribute it in column 3 and column 4, which means that if you arrange any other factors in column 3 or 4, it will confound with the interaction AB, which is not good if the interaction AB is strong. If the interaction AB is negligible, very small, just like the example, the joint account between me and my wife, that all the money earned is from my wife. So I can conclude that the increase or decrease of the joint accounts are all due to my wife, not me. Same thing. If the interaction AB is negligible, very small, then you can arrange some factors in column 3 or column 4 without worrying that there might be some interactions. If there are interactions, we will run into trouble by using the effect plot to derive the optimum design. Remember, if we are using effect plot to derive the optimum design, we assume there is no interaction. Otherwise, the prediction will be incorrect. So be careful. When you look at the three-level interactions, you will know that the interaction will happen in 2 columns. Then, by look at the textbook or some other reference, you can always find out an interaction table for pretty much most of the orthogonal array. This is the interaction table for L16, which can be used for 15 two-level factors, right? You just need to use the table to find out any interactions, the confounding columns for any interaction. And this is for L27. Again, you can see all the interactions they are happening in 2 columns, right? In 2 columns, remember 2 columns. But there are some special orthogonal array like L18 and L12. They are very special, and you will not find the interaction table. The reason is why they are special, because during the arrangement of the orthogonal array, these L12 and L18, they evenly distributed all the interaction to all the columns. Why do they want to do that? Since we don't want the interaction to affect the selection or the determination of the main effects. Since we want to use the main effects, we want to use the effect plot to find out what is the good choice for the factorial level. But if they are interactions, we cannot make the decision since they are confounded together for the main effects and interactions. As I just explained, if the interaction is very small, negligible, which is good. Why? If the interaction is negligible, then even though the interaction confounded with the main effects, the inference can be neglected, very small, which means that hopefully the inference will not affect our selection of the optimum level. That is the reason why L12 and L10 are so special. As to how to get this L12 and L10 in such a way that all the interaction can be distributed evenly into all the columns, we will not introduce that part in our class. Right. But there's a drawback, which means that if you are using L12 and L18, if you are using L12 or L10 in your design of experiment, you cannot analyze the interaction, which means that if you are using L12 or L10, you cannot use the experiment to draw the interaction plot. Very important. You cannot use L18 or L12 to analyze the interaction plot. We often use interaction plot to determine how strong the interaction is. But if you are using these two special orthogonal array, because all the interactions are evenly distributed to all the columns, you cannot use our previous method to determine whether the interaction is strong or weak. And also that is the reason why many engineers prefer to use L12 if they are using two-level factorial experiment, and L18 if they are using three-level experiment, because they kind of neglect the inference of interactions. And they first assume the interactions are negligible because during to the design of the experiments, all the interactions are evenly distributed to reduce the inference. So we can use this analysis of mean to find out what is the optimum design. If you are using the verification of experiment and you're using the adaptive model to compare the prediction result and the actual result, and you find out this two has a big difference, then you are in dead end, which means that this optimum combination is not usable. And you cannot use this experiment to find out whether there is interaction or not. There is interaction, but you cannot find out which interactions the inference are coming from. You cannot find out what is the interaction for A, B, A, C, A, D, any interaction. You cannot use L18 and L12. If you are using L18 and L12, you cannot use the experimental data to find out the to find out the interaction plot. What do you do? If you want to analyze the interaction, you need to use another table. You need to redo all your experiments. Okay, it's very important. And this is the L12. All right. So what do I mean by evenly distributed? If you are using, put some factors in column 1 and column 2, and it tells you that the interaction between the factor in column 1 and the factor in column 2 will be evenly distributed to the rest of the columns, which is column 3 to column 11. As I mentioned, if you want to study the main effects only, using L12 is good. But if you want to find out if there is interactions in your experiment, then you cannot use L12. Same things for three level. Same thing for three levels. If you are using three-level factorial, L18 is good because the design of experiments try to reduce the inference of interactions by evenly distributed all the interaction to the rest of the columns. But if you are after you verify your experiment, your optimum design, you find out that the prediction using adaptive model and the actual results are very different, then you can conclude there may be some interactions. but you cannot use the data from the L18 to analyze how strong the interaction is. This is where we were last week. Any question? We talk about if there are four factors, A, B, C, D. They are two-level design, and you put A in column 2, B in column 3, C in column 5, D in column 6. And I ask you to find out the confounding structure. Some of you didn't answer the question correctly because you didn't give me all the interactions for these four factors. Remember, I mentioned there are four factors, A, B, C, D. For two-level factors, for two-way interactions, the number of two-way interaction will be C by 2, which means that you should have 6 two-way interaction. Then you need to write down all the interaction for me, and they are total 6 two-way interaction, such as AB, AC, AD, right? And BC, BD, and CD. There are total 6 interaction. But some of you only analyze some interactions instead of all the interaction. There are supposed to be 6 interactions, so your confounding structure is incomplete.